Good morning, good afternoon, and good evening from wherever you're joining us today. It's my absolute pleasure to introduce our opening keynote speaker, Professor Deborah Hughes Hallett. Deb is a professor of mathematics at the University of Arizona and an adjunct professor of public policy at Harvard. She's known around the world for her work on improving how mathematics is taught and learned and bringing people together across the math education community. Now, I've had the privilege of hearing Deb speak many times. And every time I do, I leave feeling inspired and thinking differently about how we teach mathematics and how we can do it better. And I believe her talk today, How Will Mathematics Be Learned in the Age of AI, will resonate with many of you. This topic couldn't be more timely, especially as we all grapple to understand how AI will transform education, what it means for teaching, for learning, and for the future of our students. And as you listen, please feel free to add your questions into the Q&A or to the chat. Please join me in welcoming Professor Deborah Hughes Hallett to the Maple Conference.
Thank you. Hope everybody can hear. I know there have been comments in the chat that people were finding it difficult to hear. If you're finding it difficult to hear me, please put something in the chat, and I know some clever person will fix it. Okay. So I'm Deb Hughes Hallett. I'm going to talk for a bit about the view of teaching mathematics, not from an on-the-ground perspective so much as looking back into history and thinking about what previous changes have led to and what might be in our future. So this is a view from the balcony in some sense. Much of the world is extremely concerned about the impact of AI, how it's going to change jobs, how it's going to change education, how it's going to change lots of things. I want to say that those of us who are involved in teaching mathematics have, I think, an advantage to thinking about this in that we have gone through several changes already. And I want to look back at what those changes are and what they might tell us about the future. And this is specific to mathematics, to Maple users, to those of us who care about how mathematics is done and how it's taught. Starting historically, here is something from several thousand years ago from how the Incas worked out their mathematics. It's their technology. It's not electronic. It's not used very much now, but it is the product of a previous civilization on how mathematics can be done. I'm going to move somewhat more towards the present day, slowly. I want us to think about the technological advances in the teaching of mathematics and how they have affected the mathematics that we concentrate on. I'm not at the moment so much thinking about what changes have they made to the actual teaching method. I'm thinking about what those changes in the teaching method mean to the mathematics people learn and do. So I'm focusing back again on the mathematics. I'll look at the history. I will also peer into the future. I don't know any more than you do about exactly what's going to happen, but we can get some guidelines from our mathematical pasts. So I'm thinking about the past. First, let's go back 165 years ago. This is a Harvard entrance exam in the 1860s was find the square root of 104.8576. Remember, there were no calculators, there were no computers, there was no Maple. How were the students in 1860s supposed to do this? Well, they did have log tables. They did have awful approximation methods. But the thing I want to focus on, besides the fact that I think most of us would not have got in easily to Harvard in the 1860s if we had to do lots of things like this, what was the point of this question? The point of it was being able to calculate the square root. There was no application. There was no conceptual understanding. It was, could you do this thing? There's been a huge shift between 1860 and now about what we teach students. We're mostly not focusing on finding the square roots of awful numbers because people can do it easily on their calculators. They can do it on their phone. They can do it on the internet. The focus has changed. In this case, I think for the better, but that's a matter of opinion. Let's look at what has happened since. So now moving slightly more towards the present day, let's look at the days BC. BC in this case is before calculators. This was an era I grew up in. Many of you maybe never saw it, but it was there. And in those days, finding products of messy numbers, and real numbers are very messy, and finding quotients of real numbers were pretty grim procedures. So what did everybody do? What did students do on homework, on exams? It had the effect, for those of us who were teaching and learning in those times, that actual calculations were pretty grim affairs, and they took a lot of time. And it meant that if you wanted to do applications, they really had to be sanitized. The numbers had to be made polite, small, and integers. Real data was very hard to deal with in the BC days. Many of you, some of you, may remember or may not remember these things. I grew up on these things. Doing calculations in the BC days involved, in many cases, either log tables, which were tattered pieces of paper that you carried around in a pocket, or slide rules like this, where you could multiply messy numbers by adding and subtracting lengths, basically mechanically on the slide rule. And if you were interested in how this worked, in fact, that you were adding and subtracting logarithms, and that was why the slide rule worked. We were probably taught that it was working that way, but most of us, I think, didn't worry about how it worked. We just had to use it. So these were all necessary for school kids, for grown-ups, for all kinds of people in the BC days. Things have changed. I would say, fortunately. The first thing that happened was the four-function calculator. And this was coming in the early 70s. Now what I want to think about for each of these changes is how these changes affected what we did. In the case of four-function calculators, the initial reaction was frequently a pushback. Now, did everybody love slide rules? No, but they did have one great side effect, which was with a slide rule, you basically figured out the order of magnitude of the answer so you knew where to put the decimal place. Figuring out orders of magnitude was very useful, and it kept you from doing crazy things by making mistakes, by getting the orders of magnitude wrong. So we were forced to do orders of magnitude. With a calculator, you just typed it all in, and if you put the decimal point in the wrong place, you might never have noticed. Okay, so there was a pushback. What will happen to students' ability to do arithmetic? they will not know their times tables. And they won't be able to estimate the magnitude of an answer. True. Now, was the trade-off worth it? The students were very clear that this was better than what they had before. And indeed, their times tables and their ability to do arithmetic did wither to some extent. Was this a disaster? Should calculators be banned? It had the effect, it started to have the effect, that the focus moved away from pure computation, like the 1860 Harvard exam, towards the meaning of the computations, somewhat towards concepts and applications. Was that important? In many ways, yes. It helped answer the question for many students, when will I ever use this? Because finding square roots of nasty numbers was not obviously useful to many students. What happened next? Then we had the scientific calculator. I'm doing them separately because they did provide some difference. You can imagine there was the same concern. People's arithmetic would wither. It had the effect that log tables finally went away. And having grown up on log tables, I'm not sure I'm sad. Okay. I found logarithms useful, interesting, but I wasn't sad to lose them. This scientific calculator had a big effect in that the student's ability to do arithmetic was no longer a barrier to entry to mathematics. It had been an important barrier. If you couldn't do arithmetic, you couldn't do much else in mathematics. There were many students, to some extent, I think I may have been one of them, who find keeping all my numbers straight in a calculation hard to do. We could think conceptually, but keeping the arithmetic straight, much as Laurent said in an LLM, it doesn't always keep the numbers straight. So scientific calculators made a big difference. There was also a reaction, and some of this is still going on, that these shouldn't be allowed. And pulling up this drawbridge to make sure that the people who can't do arithmetic don't get entry into the citadel is, in many cases, is some still in operation. You can't use a calculator on exams. Whether this is good or bad, I'm not saying. I don't even think there's a single answer. But the reaction in the community was and still is that calculators are not to be used in some places. Let's go on. I want to think a bit about what this might mean for the kinds of questions we ask. For example, earlier this semester, so this is very recent, this is a month ago, the issue came up of, we're talking about autonomous vehicles, how many deaths there were in the US in the last year owing to vehicles. And the answer was 39,000, whatever. It's the number on the screen. How do you visualize that? One important way of thinking about it is to think, how many deaths per day were there? So to do that, this was in a year, you have to divide by 365. Long division is a possibility. Estimation is a better possibility. In the current day, taking out your phone and figuring it out is an even better possibility. So roughly, if you do the calculation, you could do this by hand. Most students today would not do this by hand. You might want them to, but they would be unlikely to do it. They'll pull out their phone and do it. And it's about 100 a day. This is vehicle deaths in this country, in the US. In the rest of the world, you have different numbers, but they are probably not zero. It's for an hour. Demonstrating, dramatizing what these numbers mean does involve calculation. And I would say that the calculations are better done by the technology that we have than insisting that everybody do it by long division. Okay. This, of course, doesn't require a scientific calculator. That would be done fine on a four-function calculator. If you're trying to teach students about present values of financial transactions, which is very, very important in climate change, which is very, very important to many students, you want to be able to do calculations like this. So this is not particularly applied, but just if you want to find the present value of a 1 million transaction 40 years in the future, what do you get? You need to be able to do calculations like this. The 10 to the 6 is the million, and then the present value is calculated by dividing by 1 point something to the 40. That would be an extremely unpleasant calculation done by hand. You could, in theory, do it, but oh no. And it's important here for people to see the effect of changing an interest rate. This has been one of the great debates in climate change about how the discount rate changes the present value of future benefits or future costs. The huge sparks have flown about these issues, and the calculations, you don't want the calculations to take center stage by when students are thinking about what these numbers mean. You want the numbers to take center stage. And the answer is the discount rate has a massive, massive effect on the present values. The scientific calculator does a great job. Your phone does a great job. Most students would be unable to see what the numbers meant without the technology. So the technology has changed what we can focus on. We can focus on the climate change and the impact rather than on doing the calculations. And Maple has played an enormous role in making that easier to do. Let's go on. The next thing that happened to us, all of us, was graphing calculators. I'm getting to computer algebras and Maple in a minute. Okay. And the pushback is clear in some sense. These articles, these are actual real articles. In 1982, before the graphing calculator, this is a disk with a college education, meaning that what we had usually done in college was now able to be done on the computer. What does that mean? And then later, one of my colleagues wrote a calculator with a college education. It's the same idea that the calculator can do quite easily things that had previously been the focus of mathematics. Much as in 1860, Harvard wanted to know whether the people they admitted could do square roots of awful numbers. For many years, up until the early 80s, we had spent a lot of time teaching people how to do graphs of functions. And I don't know if any of you are old enough to remember these things, but the procedure for finding a graph was, this is in the pre-graphing calculator days, was awful. You had to find intercepts. That means you have to remember what they are. Then you did these little you divided the x-axis into pieces, and you got little smiley faces going up and down that gave you the increasing, decreasing, and also the concavity in these different places. Most students doing this, if they ever got to the end, had totally forgotten what they were doing. I remember it vividly in that if I wanted somebody to draw a graph to illustrate an integral they were finding, I would have to pay them in points to draw the graph. They never did it voluntarily because it was just dangerously unhelpful and they could never get it right. So the graph was an end in itself, and it was, for most students, a rather painful end in itself. Graphing calculators changed this completely, because now, assuming you could type in the function, which wasn't that difficult, graphing calculators would happily draw the graphs. So I no longer had to pay people in points for drawing graphs. They used to do it. That helped understand whether you expected an integral to be positive or negative, whether you expected the pieces of the area under the curve to cancel out or not cancel out. It made a huge difference in understanding what a function behaved like and what impact that had on integrals, derivatives, and so on. This made a huge difference. And a lot of it had to do with the fact that although by this time Maple could easily draw the graphs, in high schools, in middle schools, most students didn't have access to that, but the graphing calculators quickly took over in that respect. Now, again, there was a lot of pushback. It made graphing easier. It made students sometimes use the graph voluntarily. But there were, again, predictions of disaster. People won't know how to draw graphs. They won't know the shapes of graphs. This turned out, the worries were true. It wasn't, the worries were not unfounded. I would say that what we should think about is not whether the worries were unfounded. They were not unfounded. The worries were what happened next. Is it worth what we got for it? There's a trade-off between being able to do this by hand and what you can do if you use technology. We've settled in a sort of equilibrium at the moment, temporary perhaps, which is the AP exams, the advanced placement exams, a lot of the public exams in the US do allow graphing calculators on part of it. So people have the incentive to learn how to do some things by hand, because not all of that you can do with a graphing calculator. And they also have an incentive to learn how to use the technology well. And there's a certain amount of research that says that the students who are judicious about how they use it or when they use it are actually doing the best. The people who use it all the time are not doing it so well, are not doing so well. The people who use it never are also not doing so well. But using it where appropriate for a student is very powerful. And again, the focus shifted away from doing the calculations, doing the graphs, to thinking about what the graphs meant. In every case, there's a trade-off between knowing how to do the things by hand, and it takes up most of your mental energy, and being able to do it easily and seeing some change in the types of problems that we would ask. And let's look at a couple of examples. Here's a cubic. What's the inverse of 20? Solving a cubic equation would not be a reasonable way to go. If you only want to estimate the answer, you could do it numerically. If you look at the graph, it's actually pretty clear. You can do this on a graphing calculator cheerfully. And you can see that the answer is about 2.5. Yes, that may not be exact. You can zoom in on a calculator and find it more exactly, but you can find it out. Another example, where is 4 to the x greater than x to the 4th? Well, actually doing this symbolically is not possible. But if you look at the graphs, you can see quite easily both the zoomed in version on the right and the far off version on the left. So you can see approximately that this is a reasonable answers for the question. And it does also show you that 4 to the x eventually outpaces x to the 4th easily. That kind of understanding about what exponentials versus polynomials is kind of useful. Another example, what is the period of this? Well, you could figure this out. You could learn formulas for doing periods. If you look at the graph, it's quite easy. The answer is pi. I'm advocating this not because the old way of doing things was bad, but because you can get students at quite an elementary level to think about new problems earlier. Here's an example. Think about the second one, ln x over log x. Think about what you expect to see and why. And when you look at it, you say, oh, that's a straight line. Yes, it is. And it's got 2 holes in it. Why? So thinking about what the graph tells you about the function tells you a good deal about logs. And I would say more useful than log tables, but whatever. What happened next? So thank you, MapleSoft, for bringing Maple in much earlier than calculators got there. Having computer algebras that actually could follow mathematical rules correctly was and is wonderful. You inspired really the calculators to come into the classrooms able to do symbolic manipulation. So for research, for scientific use, clearly Maple is far better. For teaching hundreds of thousands of school students, the Inspire broke ground. What effect did this have? Computer algebras clearly got started long before they ever hit the classroom. But when calculators came that could do computer algebras, then there's the same kind of change as we saw with the graphs. It used to be that math teachers in universities and in schools spent forever teaching people to do symbolic manipulation. Sometimes we were successful, sometimes we were not, but we tried. Having a computer algebra actually changed that quite a bit. Now the focus could be on what does this mean rather than how do you do it. This is a shift that has not totally taken place. We're in the middle of it. Thinking about symbolic form and away from the strict manipulation of the symbolic form is something that many students, many teachers, many programs have not fully made that shift yet. As a result, one of the gatekeepers, this is again in the US, it's probably different in different countries, is the public exams, the advanced placement, whatever. CAS are not allowed on those exams. And as a result, Texas Instruments had to produce 2 calculators, one with the CAS and one what didn't. Good. Perhaps that may change. One of the most important skills, I would claim, that you as mathematicians, that you as scientists, that we as mathematical people have is the ability to interpret a symbolic form. I think that you're possibly aware, I've had many examples for those of you who teach in universities, of having students come and ask questions and realize that they have made some kind of computational mistake. And you know, because you can look at the formula, you can look at the form of the expression that they have, that there's going to be a catastrophe later. Something is going to go wrong. They're going to get to a quadratic that has no solution or something. And they, because they don't see the symbolic form, they don't see the pitfall that they're about to fall into. We can look ahead and see what might happen because we can read the symbolic form. That skill of reading symbolic forms is very important. And in many ways, I hope that Maple and computer algebras in general will help us get there and change the focus from doing the manipulation to seeing what manipulation is reasonable. A couple more examples. One, use computer algebra to find the derivatives of these things. You will get 1 over x in all 3 cases. What does that tell you? They differ by a constant. And it's useful exercise for students to see how the log rules tell you that this is true. A more obscure and messy example is, look at this, the lower example, inverse tangent of some dreadful expression. Find its derivative, unpleasant at best, and graph it. You get the following graph. You can see that if you could do the symbolic manipulation, you must have gotten a function that is piecewise linear and has slope 0.5 or minus 0.5. That's not obvious looking at the function, at least to most students. And computer algebras help enormously in seeing interesting things like this. They're wonderful exploratory tools. Now I want to take a break and think about the future. I want to collect your picture of what happened with each technological innovation. There was excitement, pushback, predictions of disaster, that basic skills would be lost. And those were usually directed to the skills that had been a central focus. And I want to think about this. So those of us who are in education have previously treasured the skills that we taught, whether it was graphing functions, finding derivatives, whatever. We were often worried by the fact that the technology seemed to undermine them. Now switch to the student's point of view. They are unimpressed to be taught a skill that the technology can do happily. Why? It makes the students before us question the value of the skill. It's one thing to teach algebra and methods of integration in a world in which the only way to do it was by hand. Then you are teaching something that students would use to reach higher scientific heights. To teach the same skill in a world where this can be done on your phone is less appealing to the students. I think we have to change how we think about things to engage the students that seems like in something that seems like a worthwhile, important skill. In every case so far, and I think this will be true for AI, the shift with the technology has been towards asking different questions, not just the old questions where we don't allow people to use the technology because the technology can do the questions. We want to think about what questions should we be asking. This is a research area that is absolutely not well understood. And I'm hoping to provoke, nudge some of you into thinking about how this might happen. Many, many minds are needed here. How can we ask better questions, new questions, in a world where we have AI and Maple and many things? Before we do this, I want to say a moment about what people are using AI for. So this is not part of Maple. This is just in general, because our students come to us knowing a certain amount about what AI is doing. They use LLMs to write emails, analyze data. Lauren is quite right. They may make some mistakes, but they use it anyway. It's a lot used for making people more efficient in entry-level positions. I don't think that's going to change. Here's some data. What are people using AI for? This is the top one is percentages. The bottom one is what they're actually doing with it. Largely, it's writing communications and doing administrative things. And as time moves, what you can do with it is changing massively and quickly. And I think we need to know that students come to us having done a lot. What's using it most? Okay. Computer, mathematics, management, business, finance. The places it's used are not unexpected. Those are our students. Half of them come in having done, almost half of them, and this is last year. It's probably changed a lot by now. We may think that AI has taken over very quickly. It has actually, but compared to the internet and computers, it's similar rate of adoption. We feel like the world is whizzing by, which it is, but it's also whizzed by at various stages in the past. The point I want to make by this is that students are already using AI in lots of ways. They may or may not be mathematical, but hoping that they won't use it is not likely to be productive. So where are we now? In many complications. So here are some thoughts about where we are. And again, I'm not going to tell you where we're going because I don't know either. I'm hoping that many of the listeners here who are doing important scientific, mathematical work in many areas of the world will start to think about what questions what questions can we sensibly ask students in a world where they already know how to use AI and they already know how to use things like Maple and so on. One of the differences I see is that even with Maple and a computer algebra or whatever, students have to think about what method to use. Now, some of the time, the math teachers have undermined this by saying, use this method to do this problem. But in many cases, we don't have that prompt. You just say, find this integral, find the maximum of this function. The student has to think about what method to use. No longer. AI will mostly tell you, not always correctly, but wait a year from now and it will be more correct. We do have to have, this reflects exactly what Laurent had said, we do have to have students check that the output is reasonable, because it sometimes isn't. A huge question, this is a research area which is absolutely not answered. What do people need to know to be able to check that the output is correct? you might say they have to do everything by hand first, and a certain amount of that is absolutely true. How much isn't known, or at least not to me. So this ability to critique the answer is going to be even more important than it was already. It was already important, actually. But now it's vital. But it's an area that I don't think is well understood. And the other part is students have to be able to answer, they have to be able to ask the right questions. That's not something that they've often had to do before, because usually we ask the questions and we told them what to answer. Now, the ability to ask their own questions, to think about what information they're missing, to think about what information is needed, to think about what would be useful, to some extent, I think is going to be moving to the students. These two bottom points, what do they need to know to check that output is correct, and how to teach asking the right questions, I would say are not known. It's not clearly known. I would like to see us as a community, MapleSoft and all of you in different corners of the world, thinking about what it is we need to know, what it is we need to do to have students be able to check their answers and be able to ask good questions. Those are increasingly going to be important to people for whom the calculations can be done by Maple, they can be graphed by Maple, they can look at all kinds of symbolic expressions. But we need to have them be critical about what's a sensible answer and what's a good question to ask. Some features that I would like to see in new problems, and I think are probably important. We want to have problems that involve reasoning, not calculation. Calculation is important, but that is going to happen. You want to have them comparing models, arguments, assumptions. In many ways, we want a partner between the student and their AI. It's not just the AI doing it for the student. It's not the student doing it completely by themselves. The big issue, as you know, is that anything we think up now is definitely useful. How long it will be useful is anybody's guess. This AI is getting better quickly, very quickly, and having it slow down is not likely to happen. Given where we are, I want to point out that the two pictures on the right were generated by AI. They are mathematically horrendous. They have tons of mistakes in them, and some of them are nonsense. That, I suspect, is temporary. If I did this a year from now, I suspect I would get different pictures. So we need to think hard, we need to think quickly. We need to think about how students should check what's reasonable. We need to think about how to ask good questions. But we also need to be aware that the world is racing by and that AI will itself be able to decide, probably not too long, whether an answer is reasonable or whether or not a question is a good question. So we need to think, and we need to be aware that the world is changing fast around us. I absolutely appreciate the initial points about pairing generative AI with Maple. Excellent point. I completely appreciate using Maple to check Gen AI output. And that aspect of having the generative AI paired onto the AI, sorry, the MapleSoft paired onto the AI so that the calculations are reliable is wonderful. I think the second piece of having it check the output is having Maple check the output is actually important because the students are used to starting in AI.